Hello and welcome back to Chemistry It Is All That Matters, and we will continue our study of the gas laws, and this time we're going to look at a variation of the ideal gas law using density and molar mass as opposed to moles and volume as we saw in the first video on the ideal gas law. So let's begin by looking at the values in the ideal gas law for density. So we're going to have the equation as Pm equals dRT. P is pressure, as we've seen before. M is going to be our molar mass. D is going to be the density. R is the gas law constant, which does not change. And temperature is going to be in Kelvin, as we've seen before. Now the molar mass is the mass of the element or molecule from the periodic table, which we have looked at before, and a reminder that density is the mass divided by the volume. So density is grams over liters. That will be the units we use for this. Our R is the gas law constant, and that is 0.0821, and atmospheres liters over moles Kelvin, and we'll actually see how that will cancel using density and the molar mass. Pressure is in atmospheres, and our molar mass is in grams per mole. And once again, whenever we use the temperature in the gas laws, we must convert to Kelvin. All Celsius temperatures are converted to Kelvin. So here we have a sample problem. A gas has a density of 1.70 grams per liter at STP. What is the molar mass of the gas, and what gas is it if it is diatomic? So if we look at the values, the pressure will be 1 atmosphere, reminding ourselves that at standard temperature and pressure, we have 1 atmosphere of pressure. Molar mass, that is what we're looking for. The density is 1.70 grams per liter. That is given to us in the question. 0.0821, this is the gas law constant, atmospheres liters over moles Kelvin, and STP, the standard temperature, is 273 Kelvin. So our equation is Pm equals dRT, which we have 1 atmosphere times the unknown molar mass equals 1.7 grams per liter for our density times the gas law constant 0.0821 times the Kelvin temperature of 273. Rearranging that algebraically, we get 1.70 times 0.0821 times 273 divided by 1 atmosphere. Now what you'll notice is the liters will cancel, atmospheres will cancel, and Kelvin will cancel. We will be left with grams and moles, which is grams per mole, and that is the molar mass value that we calculate to be 38.10 grams per mole. So this is the molar mass. Now that molar mass, we are looking for which gas is it? Well, it's a diatomic gas. So what we're going to do is take that 38.10 grams per mole, and knowing that it's diatomic, we can divide that by 2, which will give us 19.05 grams per mole. And when we look that up on the periodic table, this is the mass of fluorine. So fluorine is 19.0 times 2 would give us the 38.10. So our molar mass tells us that the gas we are using is fluorine. So let's look at another example problem. So what is the density of a sample of methane, CH4, at STP? So once again, we list our values: 1 atmosphere, pressure at standard temperature and pressure. 16.05 is the mass of methane. Carbon is 12 and hydrogen is 1.01. So there are 4 of them, so that gives us a mass value of 16.05 for the gram formula mass or molar mass of methane. We are looking for the density. Our R value is 0.0821 atmospheres liters divided by moles Kelvin, and standard temperature is 273 Kelvin. Our equation is PM equals dRT, which we can rearrange to be PM over RT equals D, since we are looking for density. So that 1 atmosphere times the molar mass of 16.05 divided by the gas constant of 0.0821 times 273 Kelvin. Now atmospheres will cancel with atmospheres, Kelvin will cancel with Kelvin, and we are going to end up with a value of grams per liter when moles cancels with moles, and grams per liters is the density value, which comes out to be 0.72 grams per liter density. So this is the ideal gas law using density and molar mass, as opposed to the ideal gas law that used moles and volume. So this is two versions or basic understandings of the ideal gas law using PM equals dRT or PV equals nRT. So keep working on your chemistry.